Okie doke. All right. So hopefully you took the time to draw um, these resonance structures. So I'm going to erase all these question marks and we're going to fill them in. So the first one is an ester. And maybe we can start out by putting in the lone pairs that are missing here in the middle. Now you see that we have a double bond. We go one atom away, we find a lone pair. So that's an allylic lone pair. The first thing we're going to do is we're going to take one of those pairs of electrons and make the pi bond. So we draw the head of the arrow between the sp3 hybridized oxygen and the sp2 hybridized carbon. Then we're going to take that pi bond because we can't have a Texas carbon, and we're going to put the lone pair up here. And so what we're going to end up with will be something that looks like this. For now, the oxygen has 3 regions of electron density, therefore it has a positive charge, and this oxygen on the top has 3 lone pairs, 1 bond, and therefore it has a negative charge. Give me a thumbs up if you got that. Anybody get something that looks like that? Awesome, fantastic. Okay, you guys are probably faster at it than me. Anyhow, so the next one, again, same pattern. We have a double bond, we have a lone pair, so it's an allylic lone pair. We're going to take that lone pair and make a double bond between the carbon and the 2 carbons. And then remember, there's a lone pair that's not drawn on that nitrogen, but it's there. And then we're going to draw the second curved arrow and put the electrons up on the nitrogen. And so now we're going to have a double bond here. That's not my prettiest work. Let me fix that. We're going to have a double bond here, and we're going to have our nitrogen just going to have 2 bonds like that. And so now the negative charge is moved from that carbon up to the nitrogen. And for the last one, can anybody tell me what functional group is found in the last one? Which functional group is this? Anybody recognize that functional group from a police lineup? Exactly, that's an amide. Yes, it's an amide. And so we're going to take a look at amides a little bit either today or on Thursday, and we're going to look at them in more detail. But an amide has a double bond, and then the nitrogen has a lone pair, so that's an allylic lone pair. And thus, we're going to draw our first curved arrow, make a new pi bond, and then we're going to break this pi bond. And we end up with something that's going to look like this. So what's the charge on the nitrogen going to be now? Could anybody tell me what will the formal charge on the nitrogen be? It's going to be +1, right? And what's the formal charge on the oxygen? -1, exactly. And there you have it, folks. So allylic lone pairs. So on the third one, yes, you could draw another resonance structure. So for the one in the middle, you could draw this as a resonance structure. So you would have this. Yeah, there's nothing wrong with this as a resonance structure. It's just that right now we're just doing the pattern of the allylic lone pair. But yes, that would be also an acceptable resonance structure. Yeah. All right, so let's move on and talk a little bit more about this allylic lone pair concept. It says when an atom with an allylic lone pair has a negative charge, the charge is delocalized. So put another way, one thing that you probably noticed with each one of these is if we have a negative charge overall, that means the other resonance contributor has to have a negative charge overall. If it's neutral, then what you end up with has to be neutral overall, so on and so forth. All right. So there you go. If it's neutral, it ends up being neutral. If it's negative, it's negative. And if it's positive, it's positive. That never changes. So let's move on to the second pattern that we can recognize, which is an allylic carbocation. And so the same old rationale. We have our pi bond. We go 1 atom away. So this is an allylic position. It has a positive charge, which makes it an allylic carbocation, the positive charge being on a carbon atom. And so we can always draw a resonance structure for that, like we have shown right here. Now it says that if there's multiple bonds, or multiple double bonds, excuse me, so that would mean a conjugated system. Remember that conjugated simply means double, single, double, single, double, single, alternating. Then you can draw more than one or usually multiple resonance contributors. For example, look at this one here at the bottom. Here we see that we have an allylic carbocation right here. So we can draw a resonance contributor for that. But after we do that, we end up with a new allylic carbocation. So we can draw another resonance contributor. And so you keep going until you've drawn all the possible resonance contributors that you can make for that allylic carbocation when you have conjugation. The next one, like Savannah just identified, if you have two atoms of differing electronegativity and there's a pi bond between them, then you can draw a resonance contributor for it, which you would end up with something like this. But in number 3, it says if you have a lone pair next to a carbocation, you can always dump that electron density into the carbocation to stabilize it. And so if we have this thing here where we have a negative charge on our oxygen and a carbocation adjacent to it, you can fill in the octet of the carbon and make a neutral structure. And similarly here, we have a positive charge next to a lone pair, so we could draw a resonance contributor for that. All right, again, I've gone over this, I think, 3 times already, but if you have a pi bond between atoms of differing electronegativity, again, oxygen has an electronegativity of 3.5, carbon is 2.5, and therefore you can draw a resonance contributor where you put the negative charge on the more electronegative atom. And then finally is when you have conjugated pi bonds in a ring, you can draw a resonance contributor for it. The only question that I ever get about this is, does it matter if I draw the curved arrows in a clockwise or counterclockwise direction? It doesn't matter. You end up with the same thing no matter what. So if I was to redraw the ring, right, like this, and put my pi bonds like this, if you were to draw the curved arrows in the opposite direction, going like this, this, and this, okay, you still end up here, okay, no matter what. There we go. All right, so there you go. Those are the 5 patterns. Let's see if we can draw some resonance contributors for this guy here. Well, the first thing that I notice is that we have a lone pair next to a positive charge. So we could take that lone pair and we could fill in the octet of that carbon. So what would that look like? Oh boy, drawing a 7-membered ring is a big pain. But anyhow, so we would draw 1, 2, 3, something like that. So 1, 2, 3, 4, 5, 6, 7. Yeah, that looks good. So I have a nitrogen here that I didn't touch. I have this double bond here. I didn't touch any of this. So what is that? Oops, I can draw that a little better. There we go. So what's this going to look like? It's going to look like this. And now I've got a positive charge over here. So that was the first resonance contributor I could draw. And are there any other ones you could draw? Well, I notice that you also have, a pi bond between 2 atoms of differing electronegativity. And so we could draw a resonance contributor for that. I'm not going to redraw the molecule. I'll just redraw something that looks like this. And then I'm going to copy and paste this guy. So I'll copy and paste this thing down here and just fix the structure. So if I draw my resonance arrow like this, and this is for the blue arrow, so I'm just going to go back here and put it the way it was. So I've got my lone pair here, my positive charge here, and then I'll erase this bond. And I put a negative charge here and a positive charge here. I could do that. That's another resonance structure. So if I look at this structure here, can I draw another resonance contributor for it? Sure, I have. Did you notice that there's an allylic lone pair here? So I have a lone pair, allylic to the pi bond, so I could draw a resonance contributor like this. So I could put something like this. And so I'll paste this guy again. Come on, paste. Oh boy, I'm really running out of space here. But anyhow, let me just fix this. So this and that. So then I'm going to have my pi bond here, have a lone pair here, and then I have another allylic lone pair. So I could draw a resonance contributor for that, where I push these electrons, I put those here, and then I put these back on the nitrogen. And so I'll let you draw that one final resonance contributor. So I'm not going to draw it on here because I'm kind of running out of space. But that would be a completely neutral molecule. Oh, what the heck, I'll draw it. Let's see here if I can squeeze it in. Not a lot of room, but that's going to look something like this. So let me fix this guy. So we're going to have a double bond here, and have our lone pair on here like that. There we go. All right, I didn't close my bracket, did I? So these are improper until I close my bracket. There you go. That one's kind of a tough one. That one's not an easy problem. So you're going to have to go back in the textbook and look at a few examples. And if there's any examples that you can't figure out in the textbook, even after looking at the solutions manual, just ask me in class on Thursday and I'd be happy to go over any of them with you. All right, so Katana just asked a great question, which was, is one resonance structure more stable than the other? Or is one of them going to contribute more to the resonance hybrid than another? And the answer is yeah, absolutely. And that's what section 2.11 deals with. It's assessing resonance structures, because when you have multiple resonance contributors, not all of them, so not all resonance contributors contribute equally. The key word is not. Some of them are going to contribute much more to the resonance hybrid than others. And so there's a set of rules we can use to assess which resonance structure is going to contribute more to the resonance hybrid. Let's take a look at the rules. It won't take very long. There's only a couple of them. The first rule is that the most significant resonance structure is whichever one has the greatest number of filled octets. So if we compare these two contributors here to the resonance hybrid, a question that I didn't ask you, but sometimes I'll ask this in my lectures, I'll say, which one of these is going to contribute more? And students will usually answer this one. And their rationale is they'll say, well, there's a positive charge on a carbon, and in the second one, you have a positive charge on an oxygen. Oxygen is more electronegative, therefore it's going to be less comfortable with this positive charge, and therefore this one, the second one, should contribute less. But in fact, it's the opposite. This one, even though the positive charge is on the oxygen, it's going to contribute more to the resonance hybrid, because everything in this resonance structure, everything has a complete octet. The carbon has a complete octet, and the oxygen has a complete octet, whereas here the carbon has an incomplete octet. So that's rule number one. Rule number two is that you want to minimize the formal charges. That's really all it is. Whichever resonance structure has the fewest formal charges, that's going to be your major contributor. So if you look at all three of these, the first one has no formal charges. So if you're thinking, well, whichever one has no formal charges, that's going to contribute the most, absolutely, 100% correct. If you look at the two other ones, if I call this, I'm going to call this one A, and I'm going to call this one B. Could anybody tell me why B contributes less than A? Why does B contribute less to the hybrid than A? It's not the lone pairs on the nitrogen. It's got to do with rule number one. Right? If you look at A, everything has a complete octet, but if you look at B, in B, the carbon does not have a complete octet. And so you would use rule one to differentiate between these two. So in A, everything has a complete octet, but in B, the carbon doesn't have a complete octet. So that would be the rationale there. So that's how you can rank these in order. Rule number three. So rule number three, it says a structure with a negative charge on the more electronegative atom is going to be more significant. Well, that only works when you have everything with a complete octet. So if you look at these two structures here, in both of them, everything has a complete octet. So which one's going to be the most, contribute the most? The one where the negative charge is on the more electronegative atom. And the same thing applies for the example below it. Everything has a complete octet. And so this one is going to contribute more because the positive charge is on the less electronegative element. So that's the next rule. Let's move on from there. Rule number four. It says if a compound has an overall formal charge, focus only on drawing resonance form that shows the delocalization of that charge. Put another way is don't make up more charges. Son of a God. Don't invent new charges out of nowhere. So that would be rule number four. Just don't create charges for nothing. So you see that we have one negative charge here, and then we have one negative charge here. Well, those are good resonance contributors. once you start putting in extra charges, you know, and trying to balance them out, there's no need of doing that. So you don't create multiple charges. That's also something we seek to not do when we're drawing resonance structures. And that covers all of the rules. And so let's see if we can draw the resonance forms for each compound shown here. So if I start with this one, I'm going to put the lone pairs in on my nitrogen, because remember, when nitrogen has 2 bonds and 2 lone pairs, it has a negative charge. So the first thing we see is that we have an allylic lone pair. My lone pair here. So we can start by drawing the pattern for an allylic lone pair. We make a new pi bond, and we break this pi bond and put the lone pair on this carbon. And so if we draw the contributor to that, it's going to look something like this, where we have a double bond here. And now this nitrogen is neutral, but now the carbon has a negative charge on it. Why? Because there was a hydrogen on this carbon all along, and it's still there. So now this carbon has 3 bonds and 1 lone pair. Therefore, it has a negative charge. Can we draw another resonance contributor? Absolutely, because we have another allylic lone pair. So what are we going to do? The same old pattern. We're going to draw a new pi bond, and we're going to break this pi bond and put those electrons on this carbon, what was once the vinylic carbon. Right, so we're going to end up with a lone pair here. So we have a negative charge here, pi bond here and here, and something that looks like this. Can we draw another resonance contributor? Could anybody answer that? Yes or no? Could we draw another one? Yeah, absolutely we can, right, Katana? We can totally draw another one if we put a new pi bond here, and we move these electrons up here, and we end up with something that looks like this. And there we have it. And there you have it, my friends. So those are all the resonance contributors for this molecule. If you're thinking, well, hold on, there's another one. Well, if you were to draw this one, if you were to draw this one, it just takes you right back here to where you started from. So there's no need to draw another resonance contributor. All right, does anybody see any of the patterns in this one here? Does anybody recognize any of the patterns I'm going to draw in the missing lone pair? Anybody recognize any of the patterns here? An allylic lone pair, you know, charge between atoms of differing electronegativity, anything like that? You notice that we have a lone pair next to a carbocation. So that's one of the patterns. So we could dump that pair of electrons in here, and we could stabilize that positive charge. So we could end up with something that looks like this. So now we have a double bond here, and now we have a positive charge on the nitrogen like that. If I was to label these as being A and B, could anybody tell me which one of these would contribute more to the resonance hybrid? Would it be A or B? Anybody? It's going to be B, isn't it? Right, because it has, everything has a complete octet, but in A, the carbon with the positive charge doesn't have a complete octet exactly. Good. All right. Could we draw another resonance contributor? Sure, we can draw another resonance contributor for this one. Right, we could put these electrons back here, and then we could move these ones over here. It's a conjugated system, so I'm drawing 2 curved arrows at once. But what we would end up with then would be something that looks like this, where we have that, and then we're going to have our pi bond here, and then our positive charge is moved over here. There you go. So those are all the resonance contributors that we have here. And I'm sure that at this point, you know, there's somebody who's watching, you know, thinking, oh man, my mind is a little bit overloaded. Well, what are you going to have to do? You're going to have to take a step back, go back, look at all the first principles, look at all the patterns, and then get into the practice problems. You're going to have to take a pencil, piece of paper, and try drawing resonance structures on your own. Are you going to make mistakes? Yes, everybody does. Do not be afraid to make mistakes. Okay. You don't want to make a mistake on a quiz, of course, but you want to, you know, allow yourself the liberty to make some mistakes when you're learning a brand new subject. So I just want to touch on the idea of the resonance hybrid with you a little bit more, because again, what you've got to remember is that when you look at two resonance structures, okay, you really got to understand this, is that it's not vibrating back and forth between the two of these. It's that in reality, what we're looking at when we have an allylic carbocation is that the electrons are completely delocalized across all three carbon atoms, but we don't like to draw the resonance hybrid like this a whole lot, and there's good reasons for that, which we'll get into more as the class progresses. And so we use a model, and we draw two resonance structures in this case to demonstrate the overall resonance hybrid. To bring this back to the concept of molecular orbital theory, it says that it's consistent with molecular orbital theory and that the pi electrons occupy the three bonding molecular orbitals, which has no nodes, and the electrons are spread out across all three atoms. I'm not going to ask you anything about molecular orbitals, I don't think, in quiz number 2. So don't worry about that. I really want you to just understand that we cannot draw one resonance structure that suits, that explains the entire resonance hybrid, and that's why we have to draw multiple structures. So I want to show you a couple of things here. I want to show you one more concept kind of before we wrap up our lecture today. And that is if we look at the amide. Okay, I want to look at the amide functional group with you just for a second. So I'm going to put in the lone pairs that are missing here on the oxygen, and I'm going to zoom in on the amide here. What I want you to tell me is, first of all, what's the hybridization of this oxygen? Can anybody tell me? And it's not a trick. I'm not trying to fool you or anything on this one. It's got 3 regions of electron density. Yeah, my students are so fast, right? It's sp2. What's the hybridization of this carbon over here? Anybody can help me with that one? Hybridization of this carbon. It's got 3 reds. Yeah, it's sp2. Okay. So I'm not going to ask you about nitrogen. I'm not going to ask you that deliberately, because if I was to ask you at this point, based on what I've taught you, okay, so based on what you know, you would say it's got 1, 2, 3 bonds and 1 lone pair, 4 reds. Therefore, it is sp3 hybridized. And I would have to say, it's not sp3 hybridized. So this is a very specific example that you need to memorize. So I'm going to cross this off and put sp2, and I'm going to put here memorize that the nitrogen of an amide is actually not sp3, but it's sp2. And if you're like, oh, grown, why would that be? It's got 4 reds. Come on, man. Why? Well, the reason why is if it was sp2 hybridized, that would mean you'd have 1, 2, 3 p orbitals all in a row that could overlap with each other. And what would that do? That would allow, so I'm going to erase all that because it's kind of confusing. But if I had 3 p orbitals in a row, that would allow this lone pair on the nitrogen to be delocalized. And so instead of adopting an sp2 hybridization, the lone pair, sorry, an sp3, the nitrogen in an amide specifically, which I want you to memorize, is sp2 hybridized. sp2 hybridized, and what that does, again, is it allows that lone pair to participate in resonance. Okay, and if you draw the contributor, so I'm going to draw the other resonance structure here. I'm going to pencil it in way the heck over here, which we already did it earlier. We did it just a few minutes ago, as a matter of fact. It looks like this, okay? And if I was to have just asked you, what's the hybridization of this nitrogen? Everybody would have said, well, it's got 3 regions of electron density, therefore it's sp2. And so originally you might have said, okay, well, it's sp3. So what is it? Is it sp3 or sp2? Well, obviously I told you it's sp2. So now it gives you an explanation as to why it's sp2. It's because the only way that those electrons can participate in resonance is if there is an unhybridized p orbital on that nitrogen. So this is a very specific example that I want you to memorize. And I've taught the class for a long time so that I know that once we get into organic chemistry 2, so which is many months away for most of us, that you might see the amide and say, oh boy, that nitrogen is sp3 hybridized. But it's a very specific example that you want to memorize that it is in fact sp2 hybridized because that lone pair is delocalized. I better put square bracket over here to make this a proper resonance structure. All right, so here's a little bit more of the explanation that you can see on the slide. This is what I just covered with you, so there's nothing new here for you. And so what we're going to do in class on Thursday morning is I'm going to talk to you about this molecule. This molecule is called pyridine. So this is where we're going to start up on Thursday morning. We're going to do some practice problems, and we're going to talk about pyridine and the hybridization of the lone pair on the pyridine. And then we're going to talk a little bit more about delocalization. And so literally we have 2 slides left, and that will cover the entire class. So again, what we're going to do on Thursday morning is we're going to look at this slide and this slide that will end the entire chapter. And then I want to spend a good half an hour going over some practice problems with you. And so if there's any of the practice problems from the textbook that you're struggling with, or you say, I need to practice this in particular one, I don't understand that one, feel free to shoot me an email ahead of time, or just to let me know in class, and I'd be happy to go over any of the practice problems. But I've taught the class long enough to know that it's probably a good idea for us to stop here so that you can actually have some time to practice those questions, or the questions in the textbook. And there we have it. So